In the summer of 1950, scientists at the Los Alamos National Laboratory were taking a brief pause from the atomic age. Physicist Enrico Fermi was walking to lunch with a few colleagues. The conversation drifted from a recent magazine cartoon about missing trash cans to the statistical probabilities of faster-than-light travel and extraterrestrial life. Suddenly, right in the middle of the meal, Fermi blurted out a very simple question: where is everybody? That casual remark at a cafeteria table highlights a profound contradiction in modern astrophysics. The observable universe spans 93 billion light-years. It holds an estimated 2 trillion galaxies. Even if we just look at our local neighborhood, the Milky Way alone contains up to 400 billion stars, with potentially billions of Earth-like planets sitting directly in the habitable zones of their suns. Then there is the timeline. The universe is 13.8 billion years old. Even traveling at a fraction of the speed of light, a sufficiently advanced civilization could expand across an entire galaxy in a few million years. Given that math, the sky should be crowded. We should be detecting massive engineering projects like Dyson spheres, encountering self-replicating von Neumann probes, or at the very least picking up stray radio transmissions. But we find absolutely nothing. This lack of evidence implies a gap in our understanding of how life evolves and endures across the stars. To put actual numbers to this problem, astrophysicist Frank Drake formulated an equation in 1961 to estimate how many active, communicative alien civilizations might exist in our galaxy. This document outlines Drake's variables. Modern astronomy, particularly the Kepler mission, gives us accurate estimates for the first few factors. But moving down to the biological and sociological variables, hard data vanishes. We don't know how often intelligent life develops or survives. Depending on what numbers you plug into those final variables, the math shifts drastically. A galaxy teeming with billions of civilizations quickly narrows down to a statistical funnel where only one emerges. This text outlines a primary solution to that mathematical funnel, the Great Filter Hypothesis. It suggests that somewhere on the evolutionary timeline, there is a catastrophic barrier. If this filter is behind us, the leap from non-living matter to complex cells is so exceptionally rare that it practically never happens. In this scenario, we are the exception, and the universe is quiet because we are alone. But if the filter is ahead of us, it implies that life routinely evolves to our level of technology, but is consistently wiped out before it can leave its home star system. A civilization at our exact stage of development faces multiple exit points: nuclear annihilation, severe climate collapse, or unaligned artificial intelligence could all serve as the final barrier. This is why discovering ancient, dead bacteria on a neighboring planet like Mars would be terrible news. If life starts independently on multiple planets in the same solar system, it proves the earliest evolutionary steps are common, meaning the Great Filter is likely still waiting for us. There is another explanation that relies entirely on game theory. Popularized by science fiction author Liu Cixin, it's known as the Dark Forest Hypothesis. The theory is built on 2 simple rules. Every civilization prioritizes its own survival above all else, and civilizations will inevitably expand across a universe that contains a finite amount of matter. Because the distances between stars are so massive, communication takes years or centuries. You can never truly verify if a newly discovered civilization is peaceful or hostile. A primitive society found today could experience a technological explosion and become a mortal threat tomorrow. The only rational move is to strike first. A mechanical variant of this is the Berserker Hypothesis. Instead of active empires, the galaxy might be seeded with dormant, self-replicating artificial intelligence. These automated sentinels would be programmed to sleep in the dark, waking only to eradicate any species emitting radio waves. In these scenarios, the silence of the galaxy is a graveyard maintained by hidden predators. For over a century, humanity has been continuously broadcasting our presence, leaking a growing sphere of radio and television signals out into the dark. We can hope for the zoo hypothesis, the idea that older species are simply treating Earth as a nature reserve, quietly observing us from a distance without interfering. But the Fermi Paradox ultimately forces us to confront our own fragility. Without a clear answer from the stars, the silence suggests we are navigating a universe where survival is far from guaranteed.